Okay, let's do it. Two identical conducting spheres having charges of opposite sign attract each other with force of 0.108 Newton when separated by 0.5 meters. The spheres are connected by a conducting wire, which is then removed, and thereafter they repel each other with force of something like this. Okay, the initial charges on the spheres are. So these are identical conducting spheres. Okay, having charges of opposite sign, but not necessarily the same charge. Okay, attract each other with a force of 108 into 10 power minus 3 newtons. These when and these are like separated by 0.5 meter. First of all, just write the equation for this thing. So KQQ, so K is just 90 to 10 power 9, okay, into QQ, which we don't know, so Q1 Q2 upon R squared. Well, R squared is just 1 by 2 squared. This should be the force, which is 108 into 10 power minus 3. So this thing is just 1 by 4. This goes up and becomes 4 into 9 into all that stuff. So 9 and 12, well, this gives 3, and it's got 10 power minus 12. So Q1 Q2 equal to 3 into 10 power minus 12. Okay, that's the first information that. Wait a second. No, this will be incorrect, because it should be minus Q1 Q2 equals to this thing, because one of them is negative. So this product is supposed to be negative. This is a magnitude, so that gives Q1 Q2 equal to minus 3 into 10 power minus 12. Cool. So that's one of the information we know. What else do we have? The spheres are then connected by a conducting wire, which is then removed, and thereafter they repel each other with a force of 36 into 10 power minus 3. Okay, the initial charge on the sphere. So let's just find what was the charge when they were repelling each other. So this will just be KQ squared upon R squared. Well, we already know what K is. So K is just 9 to 10 power 9 into Q squared upon R squared, which is just 1 by 2. So it's going to be 4 into all that stuff. This is our force, which is 36 into 10 power minus 3. Wait, no, yeah, minus 3. So this cancels. So just get Q squared equal to 10 power minus 12. So Q equal to 10 power minus 6, which means that the total thing would be 2Q. So that's going to be 2 into 10 power minus 6, which should be Q1 Q plus Q2. Yeah, so the net charge that they had, both spheres at the same time, that would be this thing, right? So that should be Q1 plus Q2, because charge cannot be destroyed. So yeah, that's nice. Just multiplies by Q1, that will give Q1 squared plus Q1 Q2, because we know what Q1 Q2 is. So this gives minus 3 into 10 power minus 6 equal to 2 into 10 power minus 6. Wait, minus 6 minus 12 into Q1. So Q1 squared minus 2 into 10 power minus 6 minus 3 into 10 power minus 12 equal to 0. So it's gonna call Q1 upon 10 power minus 6 as h. So h squared, in fact not even h, x squared minus, well, it should be Q1 over there, because minus 2x minus 3 equals to 0. So x equals to 3 or x equals to minus 1. Well, so both of these roots, well, yeah, so Q1 Q2 equals to 3. So according to that, if this is the charge on one of the spheres, this will be the charge on the other sphere. Nice. So that just gives like our Q1 will be 3 into 10 power minus 6, and Q2 will be minus 10 power minus 6. But it can also be opposite, so you can actually put plus minus and minus plus over there. Nice. So we just want 10 power minus 6 as one of the things. It should be B, I think. And yeah, that looks correct. Next question. Two identical point charges are placed at a separation of L. P is a point. Okay, so they are separated by L. P is a point on the line joining the two charges, so somewhere over there, at a distance x from any one charge. The field at P is E. Okay, so this should be x, this will be L minus x. Is plotted against x values for values of x from close to 0 to slightly less than L. Cool. So the following best represents the resulting curve. Okay, So should I just find the function? Well, we know it's going to be how it's going to be. Okay, so very near to any charge we will just get like infinity as our field, because like r squared approaches 0, so it approaches infinity. So at 0 and L you should have something like positive infinity, negative infinity. Well, that's shown over here. Okay, but it also okay. So is the field just the magnitude, or are we talking about the vector? I think we are talking about the vector most likely. Yeah, so it can be, no, it cannot be this, it must be the vector. Well, is this correct? No, it's not. It's linear. Well, it's clearly not linear. This thing, no way, it's, yeah, it's showing like a limit to what this field can be as this approaches 0. That's not correct. This limit will just go to infinity, which is not correct. This, it might be correct, but whatever. 6 charges are placed at the corner of a regular hexagon as shown. If an electron is placed at the center O, force on it will be, okay, so the force on the electron when it's placed in that center thing. So yeah, just got this thing. It's got q, 2q, minus 2q, 3q, and minus q. I mean, these questions are not so hard. This is like an average question which is asked. So the thing is that, well, these will just be neglected because they cancel each other up. Okay, so having a minus q over here is pretty much the same thing as having another q over here, and having a q over here is pretty much the same thing as having a minus q over there. So this just gives, well, this gives 2q, and okay, and this gives 3q. So now what? So yes, this 2q and this 2q, well, that will give a 2q like this. I mean, this force and this force, that will give a same magnitude of the resultant, so it's going to be in this direction because its angle is 120 degrees. So we can just replace these two and have a 2q over here. So this is A, B, fine, so this is point C and this is point D. And what's this point? This point is A, this point is F. So the force is somewhere in between this A to F region. So it's along OF. No, it's not exactly, it's in between this region. Along OC. Why? No, that doesn't look correct. 0, well, no, it's not 0. None of these, it must be none of these. For equal positive charges are fixed at the vertices of a square with side length L. So first of all, you need a square with side length L. Equal positive charges, 4 equal positive charges are fixed on the vertices. Yeah, z-axis is perpendicular to the plane of a square. Okay, so z-axis is like passing through it, and z equals to 0 is the point where the diagonals of a square intersect each other, which means this central point. The plot of the electric field due to the 4 charges as one moves on the z-axis. It's not that big a deal actually, just trying to intimidate us by putting it in a square and everything. In fact, it's just 4 charges. So yeah, the only thing is that, okay, so just draw it first of all. Suppose the z coordinate is something like this, and this distance, do we know what this distance is? Yes, we know, it's L by square root 2, half the diagonal. So this is only one of the charges, one of the 4 charges, and this is our point where we want to find the field. This distance will be square root of L squared upon 2 plus z squared. So the component of the field along this direction, that will be cancelled because the 4 charges are in something like a polygon shape, and this component, well, that will be added. So it's going to be 4 times whatever it's for 1 charge. So just need to find this out. So kq, it's kq upon r squared. R squared is this thing, so it's going to be L squared upon 2 plus z squared times cosine theta. So z upon all this stuff, z upon, well, yeah, z upon square root of L squared upon 2 plus z squared, something like that, I believe. Yeah, that looks correct. Yeah, k cube by r squared into 2 upon, cool. So this can be done as, but for some reason it doesn't look very correct though. Am I missing something once again? It should be 4 times of that. Yeah, I get it. So what do we want to find? The plot of electric field with the 4 charges as one move from the z-axis. So it should be like this. Yep. So this is just kq z upon L squared upon 2 plus z squared to the power of 3 by 2. Okay, so we need to find when we get like a maximum condition or something like that, which is a problematic thing. Okay, well, it's easy for this particular thing, but it's not easy for that. So we want 3 by 2. Okay, it's like square root and stuff. That's not gonna work. There must be some way to find like this. So we need to involve his z over there. Okay, let's just do this. Kq upon, this is like z to the power of 2 by 3 to the power of 3 by 2, right? So something to the power of 3 by 2. This just goes and divides it. It's going to be L squared upon 2 into z to the power of 2 by 3 plus, well, z squared upon, it should be z to the power of 4 by 3. Yeah, that looks correct. And this to the power of 3 by 2. So in order to use that AMGM thing, we need to first of all break it down. So it's going to be L squared upon 2 into 10 power. So we just want, well, yeah, that will work. So 4 into z power 2 by 3 plus L squared upon 4 into z power 2 by 3 once again plus z power 4 by 3, correct? So this will be bigger than or equal to 3 square. Yeah, you get it. So this will just cancel out and you get some value. But when does this happen? That's what we really want. So this happens when you have z to the power of 4 by 3 equal to L squared upon 4 into z to the power of 2 by 3. So that just gives z squared equal to L squared by 4. So z equal to L by 2. That's when you get the maximum. Okay, that looks nice. So at L by 2 you have the maximum thing. Next question. The charge per unit length of the 4 quadrants of ring is 2 lambda, minus 2 lambda, lambda and minus lambda respectively. The electric field at the center is, okay. Oh, so first of all what I can do is like take this minus 2 lambda over there, making this plus lambda, and this lambda over there making this lambda, because yeah, each of these will just get cancelled like that. Yeah, so this will just give us a lambda over here and another lambda. So this can just be replaced like by a complete semicircle, whatever, of linear density lambda. And we just want to find what, the electric field, right? Okay, cool. So suppose you have a charge over there is like a small section. This angle is theta, suppose to make this theta. Then this length is rd theta, so the field will be k lambda rd theta. Yeah, k lambda rd theta, well, that's the charge upon r squared times cosine theta, because all the sine theta stuff which is gonna get cancelled. So we want to be integrating this from theta equals to minus pi by 2 to pi by 2. Cool. So this is gonna be k lambda upon r squared sine, well, yeah, that looks correct. So it's just gonna be sine theta, and it's going from minus pi by 2 to pi by 2. Yeah, so this will just be, did I do it correctly though? Looks correct. Oh, this r is there, so it's r over there. Well, okay, otherwise it's correct. Yeah, so fine. So just it should just be k lambda upon r. Well, sine theta from this to this, that's gonna be 2. So it's gonna be, well, so we want in terms of this thing, so k is just 1 upon 4 pi epsilon naught, so it's gonna be lambda upon 2 pi epsilon naught r. Looks nice. And in which direction? It should be in this direction, so minus I hat, and this is the option A. Nice. Next question. The direction theta of E bar at point P due to a uniformly charged finite rod will be. Zoom in. So this is the uniformly charged rod. Okay. It's a finite rod, right? Fine. What are these things though? So this is the field. What's this point? Is this point P and E? Okay. But we want E bar. What even is this point though? I don't know. Anyway, so it's just making some angle theta. That's what we want to find. So maybe this is like EX and EY. Okay. And this is distance t that we are given, and this is, oh, so it's the triangle that this thing makes with, fine. So since this is like 60 degrees, well, it should be half of that. This would be 2d. Okay, that's nice and all. Hey, in fact, we got a formula for this thing, right? So whenever you have a situation like this, that you got say this angle is like theta 1 and this angle is theta 2. I mean, this complete angle though, this complete angle is theta 2. It is a uniformly charged rod, and you want to find the field at this point. Well, the horizontal field, its magnitude is given by k lambda upon whatever distance this thing is. Yeah, this distance, call this a. In this case it will be d, I think. Yeah, so k lambda upon d into, so for the x-axis you have sine, so sine of theta 2 minus sine of theta 1. You can check this that when this theta 2 and theta 1 thing, so if theta 2 is plus pi by 2 and theta 1 is minus pi by 2, which means this will be like an infinitely big rod. At that point ex is just 2k lambda by d, which matches perfectly with the thing. Yeah, and our ey is k lambda by d cosine of theta 1 minus cosine of theta 2. Cool. So basically all you have is that ey upon ex, we just want to find the direction, right? So ey upon ex, after doing all the algebra stuff, you just get tan of theta 1 plus theta 2 upon 2. Okay, so let's just start putting stuff into this. What's theta 1? So the first point is this thing. Okay, it's making angle negative 60 degree, so it's going to be tan of negative 60 degrees plus what's theta 2? Theta 2 is just 0 upon 2, so that's going to be the direction that the field has. I mean, it's kind of weird, but in the end this thing is more like it's just the magnitude stuff, so it's not really related with the sign convention. So these things, these are not according to the sign convention, these are just magnitudes. So I'm just gonna say it's tan 60 degree upon 2 because that's what matters. So it's just gonna be tan 30 degrees. So if we look at this diagram, our theta, well, that's just gonna be 30 degrees. Easy as that, huh? So it's an angle 30 degree from x-axis. Yes, it is. 45 degree from x-axis. No. Well, that looks correct. It was weird, but whatever. Next question. Two equal negative charges are fixed at the points 0 comma a, 0 comma minus a on the y-axis. Okay, so you got the y-axis. Very bad drawing. Two equal negative charges on 0 comma a and 0 comma minus a, both are negative, so just say it's minus q minus q. A positive charge q is released from rest at the point 2a comma 0, so it's over here on the on the x-axis. So this point is 2A, this is A, this is A. The charge capital Q will execute simple harmonic motion about the origin. Well, I don't know if it's gonna be simple harmonic because, well, just find this. What happens if this thing is x? If this thing is x, then this distance is just square root of a squared plus x squared. So it's just gonna get k, q, whatever this charge is. So it's gonna be capital Q as well. Fine. So k, q, q upon r squared. R squared is this thing. A squared plus x squared times cosine theta. So it's gonna be x upon square root of a squared plus x squared. Okay, that's the force, but actually 2 times of that because you got 2 charges. The other component just cancel away. So it's not simple harmonic motion. Move to the origin and remain at rest. Well, not exactly. Move to infinity. No. Execute oscillatory but not simple harmonic. Yes, because this function is definitely not linear. Next question. And it could be linear if you had like some restrictions like x very small to a or something like that, but that's not true. Which is not true. It's going all the way till 2a and stuff, so no, it won't be simple harmonic at all. If the electric potential of the inner metallic sphere is 10 volt, okay, and that of the outer shell is 5 volt, then the potential at the center will be what? Electric potential of the inner metal sphere is 10 volt, and of the outer shell is 5 volt. Okay, the potential at the center will be. So I guess I don't get it what you mean by potential. So it's like if you go from infinity to this point, you will have gained this much energy, something like that. And particularly of these spheres. I mean, come on, this will add 2. So if it should be equal in that case. No. The potential at the center will be. That's really bad. They did not define it very correctly though. We don't know what they mean by potential at this point, because it could be the potential just due to this thing, but it could also be due to this thing plus this thing. I guess it must have been due to this thing plus this thing. So if it just comes from infinity to this particular point, that's the energy it would have gained. Like, yeah. More like if you got a small point over there and we want to, yeah, so if it's a positive charge thing and it just moves to infinity, the kinetic energy it will gain, it must be something like that they are saying. So in that case you have to count both of them. Okay, so let's do it. Say this guy has, well, wait a second, why are we even doing this? We already know that once it comes inside the thing of the inner metallic sphere is 10 volt and the outer shell, okay, is 5 volt. Well, the inner metallic sphere, they said metallic sphere, that means that the inside, yeah, inside that there's no field. Okay, shell is 5 volt and over here is 10 volt. Okay, cool. Potential at the center, well, it's gonna be 10 volt as well. Cool. Because come on, think about it, there's no field over there, so if you go from here to here, the difference in energy, that's 0. So it's the same potential over here as the surface. But why did they even ask this question? Whatever. Next question. 3 concentric metallic spheres, spherical shells ABC of radii ABC have surface area densities minus rho plus rho and minus rho respectively. The potential of shell A is, okay, this is gonna be some bad things. So 3 concentric metallic spheres. Okay, let's just draw it first of all. So this is A, this is B, this is C. They have charge densities minus rho plus rho and minus rho respectively. So it's proportional to a square, b square, c square. Cool. A is the smallest. Yeah. So we can just say like the charge contained by this thing. Wait a second. Yeah, the charge contained by this thing. It's gonna be that density times r squared, right? I mean 4 pi r squared, but something like that. Okay, let's just do this. It's gonna be 4 pi. The first one has negative, right? So its charge is negative sigma 4 pi r squared. And we just want to find the potential of shell A. Okay, cool. Well, I mean, like the field inside that is 0, but that's not a big deal because it's thin. Okay, this thing will just be something. That's a charge over here. Charge over there will be sigma 4 pi r squared as well. I mean, like, okay, 4 pi a squared, 4 pi b squared. And this will be sigma, so it's also minus, right? It's minus sigma 4 pi. What's this? 4 pi c squared. So the thing is that once it comes over here, well, it's been acting on this, so that's going to be the potential due to this plus the potential due to that, and the okay, so it's just going to be the sum of all these. That's going to be the potential at shell E. So it's going to be kq upon r, right? So k into the charge due to c, which is negative sigma 4 pi c squared, kq upon r, I believe. So r is just c in this case. Okay, plus, in fact, we can just write k is 1 upon 4 pi epsilon naught. So this cancels. Just got a negative sigma c squared upon c epsilon naught. Well, that c cancels as well. So it's negative c upon epsilon naught. Cool. Similarly, over here, you're just gonna get, wait, negative sigma c, yeah, sure. Over here, it's gonna get positive sigma b upon epsilon naught. Okay, because there's no field acting on this thing to that thing. Yeah. So when it goes from there to there, it will have experienced force due to this thing, to that thing, to that thing. So potentials is gonna add up. Minus sigma a upon epsilon naught as well. Cool. So that should be the potential. So it's just gonna be sigma upon epsilon naught into minus c plus b minus a. Fine. So minus a minus c plus b, that looks correct. Next question. A charged particle having some mass is resting in an equilibrium at height h above the center of a uniformly charged. Wait, what? So you just have a charged particle, some mass, so it's got m, its charge is q, is resting in equilibrium at a height h above the center of a uniformly charged non-conducting horizontal ring. What? Fine. So like something like this. This is h. Uniformly charged non-conducting horizontal ring of radius r. So this has radius r. The force of gravity acts downward. Fine. Is that the orientation that they want us to put it in, or should it be like, is it horizontal though? Height h above the center of the uniformly charged non-conducting horizontal ring, okay, of radius r is uniformly charged. Okay, it's not conducting. Well, that doesn't even matter because it's just there. What can it even do? It's not inside the ring or anything. The force of gravity acts downward. Okay, that we know. The equilibrium of the particle will be stable. Okay, it will be stable. Okay, so we just need to find what is, okay, let's just do this. What's the force on this thing? It's got this ring thing. It's at a distance x over there, then this. will this be, well, let's call it radius r, so it should be square root of r squared plus x squared. So it's going to be k q, whatever charge it has, we don't care, upon r squared, which is r squared plus x squared, this is supposed to be x, times cosine theta, so x upon square root of r squared plus x squared. So this is like kq x upon r squared plus x squared to the power of 3 by 2. Okay, so since we want a stable equilibrium, potential energy must be minimum. Okay, that's one thing. What else must be the case? Well, its field must be 0. If its field has to be 0, then x must be 0. Well, that's not correct. Oh, sorry, this force, actually just put that charge over there as well. Charge particle having some mass. Well, they didn't give us anything else. They didn't give us the charge, they didn't give us the mass or anything. Okay, that's not supposed to be correct for all values of h. The force of gravity acts downward. The equilibrium of the particle, so it is already in equilibrium, that's what they mean. Okay, so just say its charge is something, so capital Q. So this will be equal to mg, that's what we want, so that will give a particular value of x. Fine. And since we want this to have minimum potential energy, what we want is mgh. Well, okay, mgh, that's the potential energy plus the potential energy to this ring, which will be kq upon whatever this distance is, just summed up, right? So kqq upon r, so it's going to be r squared plus x squared. That will be the thing. Okay, so we know what mg is, maybe we can just put that over there, so it should be kq. Okay, well, what's h? H is just x, because it's x away, that's what we want. So kq q x squared upon square root of k squared plus x squared into k squared plus x squared. Wait, what k squared? R squared. Sorry, why am I writing everything in bad handwriting? Plus kq q upon square root of r squared plus x squared. We want this potential energy to be minimum. Right. I mean, okay, it depends on the mass and stuff, but still. So it's some particular value and stuff. This is so complicated. The equilibrium of the particle will be stable. I mean, you still got that potential energy and stuff. mgh. It depends on the mass, obviously, and also the charge. We cannot just say that it will be minimum at this particular point. So for all values of h, I don't think so. I mean, like, okay, if it goes down a little bit, will it experience more force? Yes, it will. Sure, its force will be more than, okay, so what was the force once again? This was the force. So I just want, like, if your x decreases a little bit, this force should increase. Okay, that's what we want, which means your rate of change of x. Okay, so df, okay, so it should be like minus df, I don't know. So decreasing x increases your force, increasing x decreases your force, your rate of change should be negative, which, in other words, you just want the derivative of this particular force to be negative. Okay, so we don't need all of this thing, we just want the derivative of whatever this force is to be negative. At that point it will be a stable equilibrium, because it will push it up. Yeah, so that's nice. Just want this derivative to be 0. Take a derivative. Actually, just ignore this part. that doesn't really matter. So let's do it. 1 times r square plus x squared to the power of 3 by 2 minus the derivative of whatever this thing is. So it's going to be 3 by 2 square root of r squared plus x squared into 2x into x upon r squared plus x squared to the power of 3. Nice. We want this derivative to be negative, so it's obviously less than 0. Okay, well, this is a positive constant, so don't mind that. And square root of r squared plus x squared, that's also positive constant, so don't mind that. So just 1 now, then this is gone. 2 cancels, it's got 3x squared over there minus, so r squared plus x squared minus 3x squared is less than 0. So it's got 2x squared is bigger than r squared. So yeah, so we could have done all that calculation stuff, or we can just go like this. X is bigger than r upon square root 2. Nice. So if h is bigger than r upon square root 2, yeah, it will have this property. For all values of h, no. If h is equal to r upon square root 2, this thing just becomes 0. So at that point your force is maximum. That's what we get. So it's like, yeah, one of the conditions is just fail at that point. Correct. Next question. An infinite non-conducting sheet of charge has a surface area of 10 power negative 7 coulomb per meter square. The separation between two equipotential surfaces near the surface. What? An infinite non-conducting sheet of charge. So it's a big sheet of charge, like infinite basically. It's non-conducting, cool. Surface charge density of 10 power negative 7 coulomb per meter squared. The separation between two equipotential surfaces near the sheet whose potential differ by 5 volts. Come on, that's such a stupid thing. We know what the field is gonna be. It's just gonna be sigma upon 2 epsilon naught, right? Well, yeah, sigma upon epsilon naught for a conductor, charge conductor, very near to conductor, and this thing for a sheet. And this thing times the distance traveled, that's going to be the potential, right? So the potential just say is 5 volt. I mean the potential difference basically. This thing we don't know. Sigma do we know? Well, yeah, we know it's 10 power negative 7 upon 2 pi. Okay, 2 epsilon naught. I wish I remember what epsilon naught is, but I don't. So we will have to use k for now. So 2 pi, just gonna 4 pi epsilon naught into 2 pi. That looks correct. So this will just be 9 to 10 power minus 9. Oops, not minus 9, just 9 itself. Okay, so this thing is supposed to be 5. So 18 pi d into 10 power minus, okay, not minus, 10 power 2 equal to 5. So d is just 5 upon 1800 pi. Yeah, wow. Okay, these many meters, so this should be, well, we want it in terms of, okay, yeah, well, it's kind of problematic in this case. Just find out what this thing is actually first of all. So 18 upon, what's pi should be like 3.14, so 3.14, right? So it's gonna be 314 into 18. Let's calculate what this thing is. 5 upon 8, and it should be 2 3 carried on, 1 carried on, and this should be 24. So 25, yeah, 0 314 2 5 6 5 5 6 5 2. Okay, so now what? So this is like 5 upon 5.652 into 10 power minus, well, it should be 10 power 3, so it's going to 10 power minus 3 over there. So it's something like 0 point something into 10 power minus 3 meters. So it's 0 point something millimeters. So this looks correct. No, not exactly. Next question. A bullet of mass m and charge q is fired towards a solid uniformly charged sphere of radius capital R and total charge plus q. Okay. If it strikes the surface, so I'm assuming the bullet is like a point mass, something like that. If it strikes the surface of sphere with speed u, find the minimum speed u so that it can penetrate through the sphere. Oh, okay, that's weird. So we want it to penetrate through the sphere. Huh. Solid uniformly charged. Neglect all resistance force or friction acting on bullet except electrostatic force. Well, right, whatever. So we know it's supposed to be linearly related to radius. That's the force. Okay, so just do this thing. KQ upon capital R squared into, well, actually Q instead of Q I should have written Q. This is supposed to be small r squared as well. So Q into R cubed upon capital R cubed. That would be, yeah. So if it's like a uniformly charged sphere, so this will be like the density and stuff. So yeah, that's going to be the charge for a smaller core. So this is just gonna be kq by r cubed into r. That's the force that it experiences. So we just want to integrate this kq upon r cubed r minus dr because your r is decreasing, and it goes from capital R to something, say small r. Well, we want it to what? It strikes the surface so that it can penetrate through the sphere. Well, that was very unexpected. Okay, fine. I mean, it does not necessarily need to be going through the whole thing. So, okay, it just needs to reach the center basically. So it should be 0 like this. So once it reaches the center, it will just go out like nothing happened. So yeah, nice. It's positively charged. This thing is positively charged, so it's correct. So what is this that we're calculating? We are calculating the potential difference from this point to this point. It must have that much of energy, like stuff. So let's do it. This is gonna be kq upon r cubed r dr. This is gonna be r squared upon 2. That negative charge, sorry, that negative thing converts it to 0 to r, so it's gonna be r squared upon 2. So it's gonna be kq upon 2r. Okay, that's going to be the potential difference. So what's the charge of this guy? It's going to be kq. Oh, so it also has the same charge. So it should be kq squared upon 2r, right? That's the total energy that it must have lost, which is equal to whatever kinetic energy it initially had. So half m v squared cancels. It should be cubed over there. No, it's just r. So v squared is kq squared upon m. Okay, this thing can be written as q squared upon 4 pi epsilon naught m. So v is square root of this thing, so q upon square root of 4 pi epsilon naught m. Yep, I believe that should be correct. Did we do something wrong at any point? Well, it was r squared by 2. Well, yeah, it looks correct. Potential difference, yeah, I guess it looks correct. Next question. A horizontal electric field exists as shown in the figure, and a mass m is attached at the end of a light rod. This figure. So it's electric field going like in this direction. Okay. mg by q. Okay, that's a constant field in that case. Exists as shown in the figure, and a mass m is attached at the end of a light rod. If mass m is released from the position shown in the figure, find the angular velocity of the rod when it passes through the bottommost position. Okay. So like assuming there are no frictional losses or anything, so we just have to use conservation of kinetic energy most likely. Well, yeah, looks like that. So just fine. passes through the bottommost. Wait, so why are they giving us two things? Oh, so this is the thing initially, and then this is what happens once it reaches there. It's having charge plus q. Okay, so that means that you are essentially saying that the force on this is mg in this direction, but it's also mg in this direction. Okay, so mass m is attached at the end of a light rod. Mass m is released from a position shown in the figure. Yeah, we find the angular velocity of the rod when it passes through the bottom. So is the rod, okay, rod is light and the bob is massive. So yeah, it's pretty easy. So just go mg times whatever this distance is. What's the distance though? It's gonna be this thing times, well, okay, this thing times sine theta. Say it's L sine theta. So mgl sine theta, that would be the potential energy it gained at this point, plus mgl. So this is one of these distances, and what's this distance that it went? It's gonna be 1 minus cosine theta. So this is just mgl into 1 plus sine theta minus cosine theta. That's the energy that it gained, and this should be half mv squared. Cool. So this cancels, get v squared equal to 2gl. Did they give us anything about theta though? Oh, theta is 45 degree. So this s minus c just cancels in that case. Huh. Well, that was kind of weird. So it's just mgl at that point. Nice. M is released from the position shown in the figure. Find the angular velocity of the rod when it passes through the bottommost point. See, yeah, what kind of question is this? So v is just square root of 2g by l, sorry, 2gl. So omega is square root of 2g upon l. Easy as that. Next question. The diagram shows a small bead of mass m carrying charge q. Where? Which is the bead over here carrying charge q? I don't know. Okay, the bead can freely move on the smooth fixed rings. This is the fixed ring, I think. Oh, so this is the bead. Fine. Placed on a smooth horizontal plane. Cool. In the same plane as a charge capital Q. Okay. In the same plane, a charge capital Q has also been fixed as shown. The potential at the point P due to Q is V. The potential at point P due to Q is V. The velocity with which the bead should be projected from point P so that it can complete a circle should be greater than. Okay, that's really bad, this one. That's fine. The velocity with which the bead should be projected from point P so that it can complete a circle. Yeah, so it will get repulsed and it will go back. That's basically what they are saying. So it should just be able to reach this point. Once it reaches, actually not even that point necessarily, at whichever point you have the maximum potential energy. So if it was the center, it would have in that point, but now at which point do you have the maximum? Well, this radius, I mean, like the one with the smallest radius, obviously, because the smallest distance, right? So you can draw a lot of circles over there, but the one with the smallest radius, well, that will be touching it, just touching it. Well, yeah, sure. So just need to reach this point in that case. Yes, that's correct. Let's do it. So what's the potential difference when it goes from this to this? So over here the potential, that will be what's the charge? Okay, so both have no. This has charge small q, this has charge capital Q. So just got k q q upon A. That's the potential k q q by r minus the potential at this point, which will be k q q upon 4A, I believe. Yeah, so that's gonna be the potential difference, which is potential energy difference in this case. So k q q, 3 by 4 of that, and this should be equal to, so actually you just gave us what this potential is. It's V, so in this case it will be 4V. So it's got 3V equal 3VQ. Yeah, because that thing is well. So this should be equal to the kinetic energy it initially had. So half mv squared. What's the mass? Okay, they didn't give us anything. They did, but not in terms of anything else. So now this potential is, this is potential, this is velocity. So it's got v squared equal to 6 capital V q upon m, square root of that thing. Looks like this is the option. Next, a unit positive point charge of mass m is projected with a velocity v inside the tunnel as shown. Cool. Tunnel has been made inside a uniformly charged non-conducting sphere. Nice. The minimum velocity with which the point charge should be projected such that it can reach the opposite side of the tunnel is equal to, wait, what? So okay, so it's just gonna get repulsed once again, right? That looks correct. So the potential is, what's the field? The field is related to r, right? It's linearly related to r, which means the potential would be related to r squared at this point. Well, that's kind of weird. Let's just find the field first of all. It should be kq upon r cubed into r. I mean, it could have been kq upon r squared, but then you just got that thing, like r cubed upon r squared. Yeah, so it's basically this thing. So then what? That's the field. Just wanna integrate this from so yeah, just integrate this thing from r1 to r2. That will give us the potential difference. So this should just be kq upon r cubed, 2r cubed into r2 squared upon minus r1 squared. It should be negative and stuff, but whatever, you get it. So that's going to be the potential difference. Okay, so it's proportional to r squared, which means yeah, the smaller the radius, wait, what? Okay, so the smaller the radius, I mean, okay, fine, so it's just going inside, so yeah, the smaller the radius. Wait, something doesn't make sense right now. It should you just got more energy as you get closer and closer and closer. It's proportional to r squared. No, it's proportional to negative r. Oh yeah, so suppose like if you're going from r to capital R, this would be like capital R squared, and yep, that would be capital R squared minus that. So it's negatively proportional, if that even makes sense. So it's related to the r squared thing, but it's having a negative slope. So the closer you are, the more potential energy you have. So it will just be this point that has the potential energy as the maximum. So we need to reach there. This is distance r by 2. This distance will be capital R, which means that, well, I mean, they just gave us this thing, so it should be like this. So kq upon 2r cubed, what's the potential difference? R2 cubed, sorry, R2 squared, so it should be capital R squared minus R squared by 4, which is kq upon 8r, 3 kq upon 8r. That's the potential, so this times whatever charge it has. It's a unit positive charge, so it's just this thing. Wait, so you want this in terms of sigma? What's this sigma? Is the charge density? Yeah, well, unit positive charge, so okay, this is gonna get really bad. 3k, so 3 is just like 1 upon 4 pi epsilon naught. Do you want in terms of epsilon naught? Yes, we do want. Into 8r over there. What's q? Q is 4 by 3 pi r cubed into the charge density, which is sigma over there. Sigma or whatever that thing is. So cancels, just cancels as well. This cancels as well. This cancels and becomes r squared. So it's gonna be r squared, whatever this thing is, upon epsilon naught, 8 epsilon naught. Nice. So that's the potential difference, potential energy difference, both the same in positive charge. So this should be half mv square. Okay, so just got mv squared equal to r squared, this thing upon 4 epsilon naught, so v squared is just, I just hope this is correct. So yep, it should be this thing. Next question. A conducting sphere of radius a has charge q on it. Okay, conducting sphere, so that means everything is on the outside. It is enclosed by a neutral conducting concentric spherical shell. So first of all, just got this thing. Then you have another spherical shell, like that. Does this have any? Oh, so it does have thickness. So it's 2a and 3a as the inner and outer area. This is 2a, this complete thing is like 3a, fine. And this has radius a. Okay, cool. It is enclosed by a neutral, blah, blah, blah. Find the electrostatic energy of the system. I mean, okay. Find the electrostatic energy of a system. Oh, okay. So you have to deal with self energies and everything at this point. So this is gonna get complicated really bad. Well, first of all, we need to find the distribution. So this guy has charge capital Q on it. Just don't leave that. On the outside, well, it's not doing anything. The outer one, well, it also cannot affect this guy, but this guy can affect that guy. So this is something like this, right? This has minus q by 2 and positive q by 2. Well, think about it. Wait, this thing cannot affect also. It should be minus q over there. So minus capital Q, this is supposed to be positive capital Q. Looks correct. Okay, so we need to find the electrostatic energy of the system. Oh no, this is gonna get really bad. So this is A, this is 2A, this is 3A. So first of all, we need to find the self energy of a hollow sphere. Hollow charged sphere, that is. So to bring a point charge from here, from infinity to here, what's the work that you need to do? It's supposed to be the charge on this. So kq, and this distance is say r. That's the radius. So make kq by r, right? That's the work you need to do. Yeah. Well, kq dq, because this has a charge dq, then this will be this thing. And just need to integrate this small work that we are doing from q equals to 0. Yeah, so r is a constant and everything, so from q equals to 0 to q equals to something, say capital Q. So this is just gonna be k q squared upon r. That is going to be the self energy that we have with the sphere. And then there's something called, yeah, so we have to do a lot of stuff on this one. Fine, so let's just start doing it. So let's add the self energies first of all. This guy has charge q, so this should be kq upon 2 times the radius. This guy has charge minus q, so it should be minus, I mean, like, it still did positive work to bring it over here, so why minus? No, it should be positive in that case, because you had to do positive work, so obviously plus kq upon 2 times the radius, which is 4a at this point, and this is another thing, so plus kq upon 6a. Cool. That's the self energy. Now we also need the interactive energy. So for this guy to going inside, right, so it goes inside. Well, till it's outside over here, it's not experiencing any problem. Once it gets inside, well, the field inside this thing is 0 as well. So it's not 0, it's not 0. Due to this thing it's 0, but not without that. So it has minus q and positive q over there. Just gotta do like this. So this has charge q, so it's got k q q. Wait, just want energy, right? So it should be squared over there, because yeah, squared. K q squared. So this is a g mm by r, sorry, k q upon r. That's the potential it would have gained going from this to this. So yeah, looks correct. What's this radius that we have? It's 3a, sorry, it's 2a. So that's this energy. Wait, but these are actually, this is negative, this is positive, so it should be minus over there. Plus, well, now this is positive, so it's good. So plus kq squared upon this radius, which is 3a. Okay, cool. That's for this thing, but you also have this thing over there. So this was the potential energy of this and that, and the potential energy of this and that. Now we also want the potential of this and that. Wow, it's a big problem. So it's going to be minus kq squared upon the radius, which is 3a. Nice. Okay, let's solve this. So cancels, this cancels with that, so just this thing. So 12 3 12 2, so 5kq squared upon 12a. Yeah, I believe that's correct. Cool. Next question. Yeah, we made almost no mistakes, most likely. Next question. Oh, so 1 hour is already up. Yeah, so I will meet you in the next video. See you later.